Yeah. Okay, so we now go to the manifold differential geometry and G structure. So we wish to understand the geometric structures in terms of differential geometry settings. So using bundles and connections and so on. Okay. Uh, so such a understanding help us to see issues in the different way. So actually, this is not central to lectures. However, you should try to relate this to traditional field. Okay, so let's look at the Riemannian manifold and constant curvature manifold. So differentiable manifold has a Riemannian matrix. So that is just you give at each tangent space in a product which is smooth respect to some corner charts. So if you write it in terms of corner chart, it's smooth. So such a manifold is said to be a Riemannian manifold, right? And so isometric embedding or immersion of a Riemannian manifold to one another is one-to-one map, or um, I mean immersion doesn't have to be one-to-one, but embedding has to be, so that which preserves the Riemannian metric. So we will be concerned with isometric embedding of M into itself usually. So not so the length of an arc is a value of an integral of some norm of tangent vector to the arc. So this gives us a metric on the manifold. Okay, and so of course the Riemannian metric is a norm on the each tangent space, but the metric here means a real distance metric here. So so isometric embedding always gives you into itself is isometry also. Okay. But sometimes if you go to different manifold, it may not be. But if you go to M itself, then it's the same. Geodesic is an arc minimizing the length locally. So that's some different definition in terms of not what you learn in Riemannian geometry, but it's actually another sort of definition. So the sectional curvature of a Riemannian metric along a two-plane gives you is given as a rate of area growth of disks. Okay, so you can kind of consider sectional curvature by considering some two-plane and then see how the area grows respect to these disks. So constant curvature manifold is where the sectional curvature is identical to constant in every planar direction at every point. So for example, so if you have a Euclidean manifold with a standard norm metric, so this will have a constant curvature equal to 0. Sn with a standard induced metric from Rn plus 1 has a constant curvature equal to 1. And so you take any discrete torsion-free subgroup gamma of isometry group, then it acts properly and freely. So then En but gamma has a constant curvature. Of course, you can say the same thing for Sn. Okay, so let's look at some Lie groups and the group action. So Lie group is some smooth manifold with the associative smooth product map. So G times equal to G with identity and the smooth inverse map. So Lie group is always some sort of set of symmetries of certain types of mathematical objects, but we will not study that here. So for example, if you look at the set of isometries of Sn, so this will form Lie group O n plus 1, which is a classical group called the orthogonal group. Okay. And so set of isometries of Euclidean space form a Lie group Rn dot On. So it is a extension of On by a translation group in Rn. Of course, this is a semi-direct product, but I didn't really write that down. But so I do mean that this is a semi-direct product with the direction is probably bi so at Rn because this is a normal subgroup. Yeah. So that's and So simple Lie groups are classified. Okay, so the simple ones are the ones which where this natural bilinear form is non-degenerate and or has it doesn't decompose. Okay, so the examples are something like GLNR and SLNR, and M and GLNC and UN, SUN, SP2N and SPIN and so on. Of course, GLNR is reductive, so I didn't include it, but uh, so some extension of simple Lie groups are also understandable. So so an action of a Lie group G on a space X is a map so that G times X goes to X so that the GH X is GHX. Okay, so this is a compatible. So this is called a left action because this left side is preserved. Okay, so order is preserved. So if it's a right action, you will have to reverse this H and Z, or you have to write it in the other right side. Okay, so then it doesn't have to reverse. I mean, I guess left and right actions are both interesting, but usually people study left action. So for each G in G, G gives us a map, G from X to X, where identity element correspond to identity map of X. Um, so for example, if you have Rn dot On on Rn and On on Sn, so these will all give you the actions. Okay. And so we will just go over the principal bundles and connections very fast. So our emphasis is on just the flat connections usually. Of course, there's a whole theory of connections which are uh, very, very deep, but we're not studying that here. So let M be a manifold and the G is a Lie group. So the principal fiber bundle P over M is a with a group G is that P is a manifold and the GX freely on the right. It could be left, but it's just this just says left, and this just says right. But you'll have to if you say left, then you'll have to change lots of some discussions. That's all. So P times G to the P. So G is written at the right side. So you take the quotient and the quotient map is actually quotient is actually M, and then you can pi is actually going to be some differentiable map, and P is also locally trivial. So that means you can cover M. So each point has some open neighborhood where the pi inverse of U is has a homeomorphism to U times G. Okay. Or in many cases, actually, you can say it's a diffeomorphism. Okay. So as an example, LMB the set of frames in TM. So frame means that at each point there's a vector frame. So you look at all the vector frames at all the points here. That gives you TM, and of course that has some topology, but I am not really explaining that. So GL and R acts freely on MN. So for each point, you can act by element of GL and R by just changing the frame to its image frame, right? So that's and then of course this doesn't change the base point. So if you can find the map from LM to M. Okay, so this is a principal bundle because this acts freely. So it's a principal GL and R action. And so P is a bundle space. You say P is a bundle space. M is a base space, and pi of X is called the fiber. So for any point, the inverse image is called the fiber. I mean, of course, the fiber means is defined for more general setting than just principal bundle, right? You can define for any other thing. So pi inverse of X will just be U times G for G and G. So U is some element, and then if you do the all the right action by all the elements, then this will give you all the elements of prime x because M is actually just a quotient space. Okay, so that's the idea here. So that's a principal bundle. And also the bundle can be constructed by this kind of mapping. So so you cover M by some open sets, and then um, so it's not all those open sets, but some open sets, and then you map you intersect you alpha intersect beta. So if you have this is not empty, then you send it to G some uh, map from U to U alpha to G alpha. Uh, okay. Maybe I should say this is intersection. Sorry. So map from so phi beta alpha is a map defined from this to Z, where U alpha, U beta are the trivial open subsets of M. So you cover M by some trivial open sets, and then for each intersection, you define this map, okay, phi beta alpha, and it has to satisfy this property for any triple. Okay, so if you have any three of them meeting, then these maps has to satisfy this. So this is called the transition maps. Okay, so once you have these, then what you do is you can glue these together, right? So you take M here and then cover by these, then say U alpha times G, U beta times G. Then you can glue the U alpha intersect U beta, U alpha times G by sending X some element G H to X HG and the right GX, right? It's okay. So I should say P beta alpha H X, sorry, right? So you multi so for depending on each point in this map. Okay, so this gives you a way to glue these parts of this with parts of that. Okay, right, and this condition is saying that it's compatible. Right? You can define a well-defined manifold using this. Right. So of course these are in some books, but I'm not really completely saying this. So let's say G prime and G are Lie groups, and the F G prime to G is a monomorphism. Then if you have a principal bundle over G prime, and then or principal bundle G over G, inducing identity is called the reduction of a structural group. Okay. So if you have this, and then if this respects the right action, respect to F, then it's called the reduction. Okay. So I should elaborate a little bit. Okay. So you have P. So you have some map. Okay, and then this is M. This is identity map. So this is some map here. And of course G prime X on the right and GX here. And of course there's a map F let's say this will be F tilde. So what it is saying is that you have some element X, then on the F tilde it goes to some point Y, and this respecting thing is that if you have a G prime here, thing on the right, then this means F G prime. Okay. Has to. So this means that these actions are compatible. Okay, so you need that condition. Okay, So then this is called reduction. So you have to have a monomorphism, okay, for this to work. So sometimes, so you have G, and then you may make it into uh, totally trivial topology on G prime. So it's every set is open. Then this is called trivialization reduction. Okay, so if it can be done, right? Uh, so G PGM is reducible to G prime M if and only if V alpha beta can be taken to be in G prime. Okay, so this is a reduction, and this gives you when this can be done is that when you can these gluing maps or transition maps are or always you can choose it to be in G prime, then you say it's a reduction. Okay, so you don't really need to look at all the whole group. You just need to look at some partial. So these are really elaborated in Kobayashi and Nomizu. I am not really saying too much on this. And so once you have a principal bundle, then you can define an associated bundle. So let's say F is a manifold with left action here. Then you can multiply P times F on the F, and then you can act on the right uh, by for UX. X is an element of F on the right, and then G inverse X on here. Okay. I think that's to make this into a left action. And then you have these conditions. So you can make it like on that right, and then of course this is a free action because it GX on P freely, so it doesn't matter what happens to F. So you take E to be the P times CF. Okay, so that's and then so pi E is now induced. Okay, so again of course, there's a map pi from P to M, but now you take a product which send it to M again. But now you take a quotient by G, but this G doesn't change the base point. Okay, so you still have a map. Okay, so pi E is induced from this E to M. Okay, and then so if you U is a trivial element, then the trivial covering, then the pi inverse of E, U is again U times F, can identify with U times F. So what I mean by equality here is some identity. So I'm really giving a very brief version of this. So the structure group will be the same here. So structure group is what you call G here. So for example, if you want to build a tangent bundle, then what you do is that GL and R will act on Rn on the left. And let's say F is Rn, okay? And then you look at the frame bundle, and then you multiply with the Rn, and then you take a quotient by GL and R, okay? So this will give you the tangent bundle here. Because you have GLNR is actually going to be replaced with just a point, okay, Rn point. Okay, so if you look at this, so before this, for P you have times G, but when you have F is Rn, then you replace with Rn. Okay, so so the fiber, I mean this inverse will be U times Rn, and the fiber will always be Rn. Okay, so in this bundle. Okay, so that can be identified with the tangent bundle in this way. Okay, so yeah, so these are all well explained in the Kobayashi no Mizu, but let me not point to okay. Also, you do get the tensor bundles. So there's a typo here. There's no T. So how do you do that? So you just look at the tensors over another error. So there's Rn here, Rn. Okay, so you can look at all the R and S, R contravariant and S covariant tensors on Rn. Okay, and then you let that F to be that. Okay, and then you do the same construction. Okay, then that gives you tensor bundles for any type theorem. I mean, so the way usually you're taught is that at each point you build these tensors and use a corner frame to glue and that kind of thing. So if you just think about it a little, then it's really the same construction as this one. I mean, this is a formal mathematical way to describe these kind of things. And let's go to connection. So of course I'm doing these connection things very fast. So PMG is a principal bundle, and so connection is some way to decompose. So you have a principal bundle where G is acting. So G is sort of, think of it as a fiber, and and let me draw some pictures that might be better, right? So you have some M is some line, think of the P is something here, and then G is acting on the right here. So you take a point U and then you look at the tangent space. Okay, so tangent space will have direction along G and then also along M. Okay, so these are both directions. So G direction is pretty clear. So you can think of it as a GU here at U. So it's a tangent space of G because it's not G but something isomorphic to G here on the right because its action is free. And then, but this direction is not defined actually. So I mean the transverse I mean the complementary subspace is not defined for this TU. Okay, so you can but do some kind of decomposition. So GU is called the vertical space, and this is called the horizontal space. And of course, we want to choice of this horizontal space, which is invariant under the right action of G. So G acts on the right. So it will give you, G gives you self-diffeomorphism of P. Okay, so it preserves its fiber. But so this decomposition in the Q use of G has to be just an image under the right action. Okay, so that's what we want. Okay, and then of course QU want to be defined smoothly. Okay, so the connection is just nothing more than this kind of decomposition. So the choice of QU. Okay, so that's all it is. Okay. And and of course from there you can describe some kind of a so if you go to Kobayashi and Nomizu, then he will then you can equivalent definition is some sort of a G valued form. So G is a Lie algebra valued form on TM. So you can think of this you can reduce that to that definition. Okay, but the original, I mean, just the geometrical definition is this without using any forms or something like G valued forms or things like that. Okay, so it's just a graphical picture of this. Okay, so then you can define what's a horizontal lift is a piecewise smooth path on M. You can always lift it so that tangent vectors are always horizontal. Okay. I mean, this can be done because it's just solving some ODE problem. Okay, so you want the tangent space. I mean, so you have some path here, and then the thing is that this path has to be lifted so that at each point the tangent space has to lie in U alpha. So that just becomes some sort of solving the ordinary differential equation, and it can be done. Okay, so so you can always lift it. So well, another thing is you can choose any. If this is initial point, you can choose any initial point here in the fiber, and then it will lift. Okay. So again, that's the same thing as an ordinary differential equation, that you can choose any initial point. Okay. Uh, and the horizontal lift is determined once the initial point is given. Uh, And of course, you can choose any initial. So given a curve with two endpoints, the lift defines a parallel displacement between fibers above the 2 points. Okay, so this is an important idea of the connections. Okay, uh, so you have M here, and then you have 2 points, and this is a path gamma. Then on P, uh, you have two fibers over this, and then you choose any point, you get a unique lift. Okay, unique horizontal lift. So therefore, this point is mapped to this, and then another point same. So it gives you a self the map from here to here, which is actually a diffeomorphism, and it's commits with G actions. Okay, of course the right G actions. Okay, because the horizontal lift can be changed by the right action, and it's still a horizontal lift. Okay, so therefore it's just some kind of. So of course details are in the book, but that's the idea. So if you fix a point, then this defines a holonomic group. So what is a holonomic group in the classical sense is that you take some point and then you look at all the paths here, ending, coming and ending here. Then you look at all the elements, all the parallel transformation here. So if you can identify this with Z, then you get a self map of Z, or you can just look at pi1 of X, and then uh, so you look at all the elements path for any loop here. You get elements here, and then that gives you a group, because this path of loops gives you a loop, and then uh, these loops gives you is a loop. I mean, it's not a fundamental group, but just a loop group, and then this will give you another group acting on pi inverse of X. Okay. So that's called the holonomic group. Uh, so far we don't need any sort of flatness for this. And so the what is a curvature of a connection? So it's not a Riemannian geometry curvature comes from this, but I mean, this is a later development than the Riemannian geometry. But what really curvature is measure of how much small horizontal loop is a small loop on a loop is a loop on P. Okay, so this is real definition of curvature in the connection sense, and of course this is more universal definition. Okay, so you take any small loop, so which is homotopically trivial usually. Okay, so actually, I mean, this has theory nothing to do with homotopies. It's just consider the loops. Then this will horizontal lift will not maybe not lift to itself. Okay, I mean maybe not lift to the identity here. Okay, this holonomy may not be identity along this loop. Okay? Even if this is not homotopically trivial. So for that to be happen, you need flatness. But if it's not flat, then locally it could, you know, uh, have some. It might not lift to a closed loop. Okay. Because that's a sort of a property of these horizontal planes. Okay, so horizontal planes may be weird, so that this even small loops doesn't lead to same point. Okay, so it doesn't become identity. So then that can be considered some sort of G action, and then you make this into infinitesimal version. Then it becomes some sort of a two form, and then this is the curvature really. Okay. So of course, formal definition is in the Kobayashi Nomizu. So the flat connections are the case when any homotopically trivial loop will lead to its identity. Okay, lead to loops. Okay, so any holonomy along the loop is so holonomy means when I go around come back to the same point, how much it moved. Okay. So holonomy is always trivial. I mean, for the locally small loops or the homotopically trivial loops, it always come back to the same point. Okay. Yeah. So lifts to the horizontal loop. Okay. So it's like the covering is actually sort of a flat bundle in this sense for the discrete groups actually. When it's a normal covering actually, right? So normal covering can be sort of in this way. Uh, So, so that's a flat case, and the flat connection gives us smooth foliation of dimension and transversal to the fibers. So because you can lift all the trivial loops, you can kind of make a connection between all these passes, and uh, and then whenever you come back to the same point. So from here you can always extend to every other point, so you get some sort of a leap. So in higher dimensions also, but I'm just drawing the two dimension in this one dimensional manifold. But you can imagine if you have a higher dimension, then whenever you come back, you get some other uh, these leaps will be well formed. Okay, so that's a horizontal. Uh, so flat foliation is a smooth foliation. Uh, Gives you actually the converse also happens to be true, but uh, so once you have a associated bundle, so you have a connection, and then the associated bundle admits a connection also. Okay, that's because if you have any principal bundle, then you define any for any two any path you have a horizontal lift. So this gives you some sort of a right action by Z, and then you can transfer that action to the associated bundle. And of course, I'm not defining this precisely. And of course, flatness is also equivalent to local lifting property. Okay, so you have associates bundle, and then suppose you can do the same sort of local holonomy here, because connections gives you a way to identify the fibers. And if it's flat, then you can actually find the foliation and so on. So therefore, flat connection will give you this foliation. Okay, so one will give you smooth foliation dimension and transversal to the fiber. N is the dimension of the manifold. Uh, so summary is a connection gives you a way to identify fibers given paths over on X bundle over M. And flatness gives us locally consistent identification. Okay, so X, I mean, here maybe I should say F. Okay, F is X here. And the principal bundle, and there's a relation between principal bundle and G structure. So suppose we have a manifold M of dimension n and the Lie group G acting on a manifold X of dimension n. Uh, Suppose we have a principal bundle P, then you can find the associated bundle E with the fiber isomorphic to X, with say flat connections. I suppose we can do that. Then the section which is transversed to everywhere to the foliation given by the flat connection. Then suppose we can do that, then that gives you a GX structure, and conversely, GX structure give you the P, E, and F and all these bundles. Okay, so I think that's covered in the Goldman's GSM 227, but I don't think I'm going to explain that completely. But anyway, so there's some relation between these G structures and the principal bundles. Okay, so for X manifolds. Okay, so this is the end of this lecture here. Uh, okay.